Okay, so this is part 2 of Unit 10, Objective 3A. So when I realized, oh my gosh, it really is going to be an hour-long video, I decided to split it over 2 videos, just so that you can kind of take a break in between. So if you haven't already, you probably should have gone through and done all your pedal graphing on the homework, just to kind of get that out of the way, and then hopefully then watch the second video. So here we go. So this is Unit 10, Objective 3, Part A still. So we're still only in Part A, but this is Part 2 of a 2-part video lesson. Okay, so we're going to go ahead and take a look at the other 2 graphs, which are the cardioids and the limacons. So the cardioid and the limacon. So for this one right here, so again, these graphs are really just kind of hybrid graphs of each other. So if you take a look at the difference between the pictures here, so the orientation can be anyway. So I would say this one is to the right because the bulk of the graph is in quadrant 1 and 4. And so this would be a graph going to the right. But it really could be a graph that is rotated 90 degrees, pointed up, left, or down. So it can go in any direction. And so these 2 graphs are the same. So they have that same kind of outer circle or outer shell. And they're drawn and graphed exactly the same. And then this one, though, has an extra inner loop here. And we'll see why that one is created. So how do you know if you have a cardioid and a limacon instead of just like a pedal graph? So the difference here is whether or not you're adding or subtracting. And so if you think of like working with the limacon in general, you can really just learn how do I graph a limacon, and then a cardioid just kind of naturally kind of falls out of that. So really your focus should be on like how do I graph a limacon. So we're going to start with that one first, because if you can graph a limacon, then you can graph a cardioid exactly the same way. Like you don't have to learn anything extra for a cardioid. All right, so let's start with a limacon graph. So again, I'm adding or subtracting. And so you're going to have 2 different numbers that you kind of have to pay attention to. So the first thing that you should look at is just kind of your orientation of the graph. So meaning, is it, going up, down, left, or right? And that depends upon whether you're adding or subtracting sine versus cosine. So what you already know about, so like kind of in your back pocket there, you know that for your sine graph, so I'm just going to kind of do that off to the side here. It is positive above and negative below because sine is your y value. So if you were adding sine, then your graph would be up where sine is positive. But if you were subtracting sine, then your graph would be down here where it's negative. Okay? So I'm going to do that down here. So if I had a adding of a sine graph, that would be this guy right there. Okay, because I know this is hard to see, but there is a axis right here and right here. And so I know sine is positive, right, up in these 2 quadrants. So this would be a picture of a positive sine graph. Whereas if you had say a negative, right, so if it was a negative sine graph, so I'm going to just do that one over here in the corner. So if I had a negative sine, that graph would actually be oriented down. So that would be a negative sine graph. So if you were to look at this one right here, this one would actually be a positive cosine. And how do I know it's a positive cosine? Because this is cosine positive here, and it's oriented to the left. And again, these are really hard to see, but there are axes right here. So this would be a positive cosine graph. So then a negative cosine graph would just be reflected across the y-axis, and so it would be over here somewhere, right? So we're just kind of tracing that one out. Okay, so that's how you tell the orientation, whether you're adding or subtracting sine versus cosine. And then we have these values here, a and b. So a is what I refer to as the constant. So a is my constant because I'm not multiplying that to anything. And then b is our coefficient, right? So b is a coefficient of your trig function. So specifically, a limacon can actually be where a is less than b or greater than b, but when it's greater than b, we learn that in the second half of the lesson, and we call that a kidney, even though technically it is a limacon still. So again, one more time, when a is smaller than b, right, then we have a limacon graph. And so like eventually you're going to have to know like, oh, A needs to be less than B. So think of that. So if A is less than B, I get the limacon with the extra circle. All right, so what do the A and the B do? Okay, so A and B, so when I add their values, so their absolute values. So if this was, say, like 2 minus 4, I don't think of that as negative 4, I just think of it as 4. So I add their absolute values, that gives me the distance across the outer loop. Sometimes I refer to that as the diameter of that outer loop, but it's not a circle, so that's like a little, not exactly technical. So again, so what are we talking about here? So this distance right here, so this is my outer loop, so this distance right here from the pole, so they always go through the pole there, is the absolute value of A plus the absolute value of B. And then if so that's what that is, and then when I subtract those values, I get the distance across the inner loop. So the distance across the inner loop, so that would be from here to here. So when I add them together, I get the outer loop. When I subtract them, so smaller, I get the smaller loop, which is the inner loop. And so we really are just subtracting the bigger number minus the smaller, right? And so I would just look to see like which one's bigger or which one's smaller, and then subtract them so I get that positive value because I'm looking at a distance. Okay, so add them for the outer loop, subtract them for the inner loop. And then what is A? So A by itself is the shoulders, so I call this the shoulders right here. So these little guys, I call them the shoulders again. Not a technical name by any stretch, but that's what I call them, the little shoulders there. And so those go out a distance of A units. Okay, so that is kind of the structure of a limacon. All right, so I am going to show you like how to graph it with a table of values and then how to graph it with what I just covered. And I'm showing you both ways because one thing that we all have the ability to do is plot points. And so next year when you've completely forgotten how to graph a limacon, you know you can always plot points. And then once you get a few points landed, you can usually then figure out the structure. And so that's why we're going to start with creating a table of values. So you can take a look at to do that part. Okay, so we're going to start with just filling in the table of values first. So I just have the quadrantals listed here because those are numbers that are easy to work with. And then I'm just going to replace theta with each of the quadrantals, and I'm just going to manually plot points to get enough so that I can figure out how to graph it without having to like memorize like up here like what A and B are doing, okay? So if I ever forget, I can plot points. Okay, so we're going to just start with theta equaling 0. So I'm going to start with that first point. So I'm going to let theta equal 0. So I'm going to take the equation, let me zoom in just a tiny bit. So I'm just going to take this equation here and I'm going to replace theta with 0. So I will still have r is equal to 3 plus 4 and then sine of 0. Sine of 0. 0 and theta look too much like. So sine of 0. So we're just looking at our unit circle here, but I just have the quadrantals. So I know sine is my y value, so when theta is 0, my y value is 0 as well. So then this would just be 3 plus 4 times 0, right? Because this guy right here is 0, so that would be just 0. So then when theta was 0, r is 3. Okay, so then I'm going to plot that point. So on 0, so this is 0 right here, I go out 3 units, 1, 2, 3. And then I'm going to do the same thing again for pi over 2. So now I'm going to let theta equal pi over 2. I'm going to take the same exact equation and replace theta with pi over 2. Okay. And so again, we're just using our unit circle. So pi over 2 is up here, and sine is my y value, and so I know y is equal to 1. So sine of pi over 2 would just be 1. So then this would be the same as 3 plus 4 times 1, which is 4, and then that would be 7. So when theta was pi over 2, I go at a distance of 7. So this circle is not big enough, so let me just kind of extend out this way right here. And then instead of doing like the full circles, I usually just kind of, just do a partial, kind of pretend that we go out a couple more. So 7 would be right here. So again, there would be actually circles, but we're just going to do little lines there. All right, and then now we're going to do theta equaling pi. So again, I'm going to take that same equation and replace theta with pi. So then if I look at my unit circle quadrantals only, so when I go to pi, I look at the y value. So when y is, or sine of pi is my y value, which is 0. So then sine of pi is just 0. 4 times 0, of course, is 0. So that would be 3. So when we get to pi, so that's over here, I would go out 3 units, so towards it because it's positive. And then one more here, so 3 pi over 2. So I would get r equals 3 plus 4 sine of 3 pi over 2. And then look here. So 3 pi over 2 is down here. Sine is my y value, so that would be negative 1. So then I'm going to replace that with negative 1. So that would be negative 4, and then 3 minus 4 is negative 1. So 3 pi over 2 is negative 1. So here is 3 pi over 2, and then instead of going towards it 1 unit, I'm going to go away from it 1 unit because my r is negative. So I'm going to go away from 3 pi over 2, so I'm going to go backwards, and that's negative 1. And then I don't have to plug in 2 pi, do I? Because isn't 2 pi and 0 the same thing here? So I know if 0 gave me 3, 2 pi would give me 3 as well. Okay. All right, and then again, a limacon always goes through the poles. So I'm going to put an extra dot there. So if I had if I couldn't remember, like just kind of like the rules of graphing, right? I always have that table of values kind of in my back pocket to help me graph. And so this gives me like enough points that I can go ahead and graph this. So when I know I have a limacon because I'm adding or subtracting. And so then now when I graph this, I'm going to graph kind of my outer heart shape and then that little inner loop. So I have that outer heart shape. So I don't always do a great job at making it roundy. It looks more pointy sometimes. And then I have that little inner loop. Okay, and normally it'd be symmetrical, but that's what you get. Okay. All right, so there's my table of values, and then I sketch the graph for part B, and then for part C and D, I actually do that together. So we're going to indicate direction, and then we're going to label the start and the stop. So this right here is, we always want to make sure that we use a different color for this when we do this, so use a different color. And you don't actually, write the word stop. So when we say label it, we mean like you're just going to put a dot. Where did it start? Where did it stop? And it's always going to be on the same location. And indicate the direction in which you're traveling. So you're always going to just use like a little arrow. And it's always going to be counterclockwise, right? Because isn't that our positive direction? So because when we go around the unit circle, right, we start at 0 and then we travel this way. Okay, so it's always going to be that. But you can also look at your dots over here if you forget that. So where did we start? We started at 0, 3, so on the line of 0 at a radius of 3. So this is my first dot right here. So this may not show it very well because I have a pencil mark already there. So that's my first dot. So that's me labeling it by just putting that heavy dot there. And then now I'm going to indicate the direction in which I went next. So I went to pi over 2, 7, so I went up to this dot next. So I'm just going to trace like a short section of the graph. So just trace that short section and then just put like a little arrow to indicate then that was the next way I went, and always counterclockwise. Okay, so again, that color doesn't show up very well because I have the pencil line already. Okay, so if you think you got that, you can go ahead and press pause and then move on to the next one to kind of check it. But before we do that, I do want to talk about, again, kind of like if you have, if it kind of makes sense and you can like learn what to do with that 3 and the 4, like a shortcut way to kind of graph that. So just to kind of keep in mind, so this is our A and our B value, right? So we talked about the shoulders, the diameter of that outer loop, and then the inner loop as well. So the shoulders are at 3. So if I look here, so 1, 2, 3, so my shoulders are at 3. If I add these together, 3 plus 4 is 7, whoop, all the way up here, and that was at 7. And then if I subtract them, 4 minus 3 is 1, and then that was 1 as well, right? So those numbers give me all of that. And then what's the orientation? So this is positive sine. So sine is positive up here, right? So if you see, the graph is pointed in that positive direction, so kind of that upwards way. Okay? All right, let's do one more limacon graph, and then we'll talk about cardioids. Okay. So I'm going to do that shortcut method first, okay? And then we'll talk about table of values second, so that shortcut method. So, all right, so we are going to actually do B first. So instead of filling the table, we're going to look at, can I figure out the graph without doing a table of values? So I know that I have a negative cosine, right? So I'm subtracting and I have a cosine. So I know that cosine is negative over here, so my orientation is going to be headed left, right? So I'm going to be headed left. So I know that the graph in general is going to like kind of go like that, right? And it will have an inner loop because these are not equal to each other. So I will have an inner loop there. Okay, so we're going to, again, just look at how would I graph it using that A and that B value, and then we'll do the table of values and plot points just to verify. So my shoulders are at this number here, so my shoulders are at 2, so that's these guys right here. So I would go out 2 circles, 1, 2, and 1, 2. I'm always going to go through the pole, so let me go ahead and mark that. And then I'm going to add these two numbers together to get the diameter of the big circle, right, the outer circle. So 2 plus 4, 6. I'm going to go 6 units to the left because it's oriented to the left. Oh man, add another little line here and another one. Okay, so wait. So here's 6. So that gives me the outer loop, right? And then now the inner loop, I subtract them. So now subtract 2 and 4. So 4 minus 2 is 2. And again, it's going to head to the left. So 1, 2. And there's my inner loop. Okay. All right. So now to do direction start and stop, though, I would have to at least substitute in 0, right? Because I need to know where was that first point located. Because if I look on 0, I've got 1, 2, 3 dots on either towards 0 or away from 0. So I don't know which of these 3 is the actual start. So I have to at least minimum plug in theta equals 0. Okay? All right, so and that's to do part C and D. So I'm going to do that work over here. So theta equaling 0. So replace theta with 0. So I would have r equals 2 minus 4. Replace theta with 0. And go to my handy-dandy unit circle. So at 0, cosine is my x, so that would be 1, right? So that would be 1. So that'd be 2 minus 4 times 1, of course, is 4, so that would be negative 2. So when theta is 0, r is negative 2. So this is 0 here, so because r is negative 2, I don't go towards 0, I go away from 0, so 1, 2. So my start is actually, again, you're not going to be able to see this because I have my pencil mark there. So my start is right here, but you can see where I'm marking. So there's my start right here, and then I'm going to go in a counterclockwise direction, right? Because that's the way we travel in a circle. So then for my indicate direction, I'm going to trace like a little section of it, and then put an arrow at the tip saying where we travel to next. Okay? All right, so that's how we would graph limacons, but we're going to go ahead and fill in that table of values as well. So as a backup plan, right? So if I have theta is equal to pi over 2, I'm just going to take that same original equation, and instead of cosine of theta, I'm going to have cosine of pi over 2. So cosine of pi over 2, so when that is your x value, so that would be at 0, right? So cosine of pi over 2 is 0. So 2 minus 0 would just be 2. So then at pi over 2, if you look at this, my shoulder is at 2, which it is, right? So this was at 2. So again, we can always plot points as well, right? Okay, and then theta equals pi. So that would be r equals 2 minus 4 cosine of pi. And then at pi, cosine is negative 1, so that would be 2 minus 4 times negative 1. And so that gives me a positive 4, so 2 plus 4 would be 6. And then if you look here at pi, I went towards pi, 1, 2, 3, 4, 5, 6. So 6 units. And then one more here, 3 pi over 2. And then at 3 pi over 2, then let's see, cosine would be 0, so that would just be 0 there. And then 2 minus 4 times 0, so that would just be 2. And then if you look here at 3 pi over 2, I'm going 1, 2, 2 units, and there we go. And then again, we don't have to do 2 pi because remember these are at the same location right here. So 0, 2 pi are at the same location. So that would also generate a value of -2. Okay, so there are limacons. And then finally, our last one is cardioids. So let's take a look at those real quick. So I'm just going to go back to that front page of notes here for cardioids. So cardioids seem to be that they seem to be different, but they're really not. The only thing that happens is because these are the same, there's not going to be a diameter of that inner loop, right? Because it would be 0. Because we know that to find the inner loop, we subtract those values. So if they're the same, that value would be 0, and then that's why we don't have that inner loop in a cardioid. So you can like think of it as like a different graph, but if you graph it the same way you do a limacon, you're always going to get the same thing, because when you subtract, you're going to be like, wait, it's 0. Oh, right. It's a cardioid, no inner loop, right? Okay. So same graph, right? Or same idea, I should say. So again, your orientation is dependent upon are you adding or subtracting sine or cosine. And then to go the distance across here, so just like your other one, you're going to add these two numbers together, right? So over here for limacons, we did the same. We added them. That gave me the length of that outer loop. So same thing. So when I go and I add these two numbers together, so a plus a, I get how long that inner loop is. If I subtract them, a minus a, how long is that inner loop, which would be 0. And then, so no inner loop, right? And so then A, of course, again, is the intersection of the shoulders. And again, that is not a technical name, so do not ever quote me on that. So I do call that my shoulders, and then that goes out a distance of 8 units. Okay, so let's do a couple cardioids. Okay, so for our cardioid graphs, so I am going to do a table of values first and graph that. And then after I do my cardioid table of values, then I will go and investigate it, doing it kind of like learning the structure of the equation to help me graph it, okay? So let's start with theta equaling 0. So I'm going to just do that off to the side over here. So I'm going to go ahead and replace theta with 0. And so I will have r is equal to 3 plus 3 cosine of 0, and I know cosine is my x value, and then at 0, x is 1. So then that would be 3 plus 3 times 1, which is just 3 plus 3, which is 6. So then that will be, so at 0, I'm going to go out a distance of 6, so I know that's not going to be long enough, so I'm just going to add like a little line there. So 0, go out to 6. And then now I'm going to do at theta equals pi over 2. And I know at pi over 2, cosine is 0. So that would just be 3 plus 0. 3 plus 0, which is 3. Sorry, I got distracted over here. Not that I did not know 3 plus 0. I know 3 plus 0. All right, so then at pi over 2, I'm going to go out to 3. So right there. And then I'm going to plug in pi. And so pi, so again, if I can look here. So pi, at pi, x is my cosine value, which is -1. So that would be 3 plus 3 times -1. Or 3 minus 3, which is 0. And that's why that inner loop is 0, right? Because we're not going to be dragging back in. So 3 minus 3 is 0. No inner loop. And then we'll do 3 pi over 2. And then 3 pi over 2, cosine is 0. So that would just be 3 plus 0, which is 3. So here is 3 pi over 2 down here, and I will go towards it 3 units. 1, 2, 3. And then, of course, remember 2 pi and 0 should land in the same spot, right? Because they are on the same line. And then that gives me enough points to get that graph going. So it's just like that limacon graph, but you're just going to get that outer loop because that inner loop had that radius of 0. So there's not going to be another right through there. And then we have to indicate where did I start and then what was my direction on that. So again, you're not going to be able to actually see the color part of it because I have that dark pencil, but you can see where I'm marking. So at theta equals 0, my radius was 6, right? So there's 2 dots, right, on here, and I need to know, well, which one did I start at? And so I do that by substituting it in. So that was a radius of 6, so that was right here. So this is my start. So you can use a different color for me. And then direction is always counterclockwise or going towards pi over 2, right, because that's always the next dot we do. So towards pi over 2, and then put like a little arrow on there. Okay, so then that whole kind of shortcut vision, which is the same as the limacon one. So I know that this will give me my orientation. I'm adding cosine. So where is cosine? Positive here. So that means I'm going to go towards the right. Yeah? So towards the right, which is this one. So then if it goes towards the right, that means it's going to be here. And so let's say I was like, oh, I don't know, do I have a circle or not? Like the inner circle. So you'll figure that out as you graph it. So your radius is, or your shoulders are at 3, right? That constant value. So 3, so 1, 2, 3. 1, 2, 3, right? That's where they were. And then you add the numbers for your outer loop. So 3 plus 3 is 6. So there's that dot right there. Subtract them for your inner loop. 3 minus 3 is 0. 0 meaning no inner loop. Okay? All right, last problem here. Okay. All right, so for this one right here, and so I would look and I would say, oh, I got a negative sine graph. Hold on. Okay. So I have a negative sign. So if I think about where the heck is sine negative, here and here. So that's the orientation, right? So that means my graph is going to be here. Okay, so pointed downwards. So let's graph it first without the table and see what we can do about that. Okay, so negative sign. So my shoulders are at 2, so these guys are at 2. So from the origin, I'm going to go 2 to the left and to the right. I'm going to have a pole point. And then I add these for my outer loop. So 2 plus 2 is 4. So downwards, right, because it's a negative sine graph. So 1, 2, 3, 4. And then I subtract them for my inner loop. So 2 minus 2 is 0, so meaning no inner loop. And that would give me that graph. Okay. All right, so that's how I can graph it quickly without doing the points. But no matter what, we got to plug in that 0 to figure which of these 3 on the 0 line is actually my starting point. So I have to, at the very least, evaluate it at 0. And then sine of 0 is 0, so 2 minus 0 is 2. So this is 2. So that means it started here, and then it went counterclockwise towards pi over 2, because that would be the next dot I would do. So I'm just going to dot here, and then darken that, and then put a little line there. Okay? And then I'm not going to fill in the rest of the table because I think you guys got that. And so that is the last of just part A. More to come.